Okay, I think we get started here. So welcome everyone to session 2B, the replay session. My name is Shami. I'm a principal research scientist at Cornell, and I've been working on FRBs for a while now, since they've been around. And it is my great pleasure to chair this session. Just a quick reminder, if you are one of the speakers and you are around to answer questions, if you're speaking live, obviously you'll be around to answer questions, but if you or a team member, you are around to answer questions, please let us know in the chat and I will mention that. And then if we don't have anyone who can take live questions or even otherwise, please do leave questions in the FRB 2021 Slack under Plenary 02. And the speakers or team members will get around to answering those questions. I think that's all the preliminaries we need to deal with. Right. So the first speaker in this session is Kenzie Nemo. Kenzie is a graduate student at ASTRON, and Kenzie is doing this live a second time. So take it away, Kenzie. I will let you know at with 3 minutes to go.
Yeah, it's a recorded talk, Shami.
Oh, Kenzie is just going to be around. Okay, very good. So I won't have to mark time for her, but Kenzie is around for questions. So please leave questions in the Q&A. All right.
Yeah, so I'm Kenzie Nemo. I'm a third-year PhD student here in Amsterdam. And yeah, I'm happy that I get to share some of our work with you today on linking fast radio bursts to galactic neutron stars through their timescales and their luminosities. So I'll begin by showing the transient phase space diagram for short duration transients. So here we have duration on the x-axis, luminosity on the y-axis. You can see the pulsars and RRATs in pink. Some pulsars emit giant pulses shown in orange. The crab has giant pulses that some of which resolve down to isolated nanosecond duration shots of emission, often called nanoshots. And then you have the extremely luminous fast radio bursts up at the top here. So the clear division that you can see between the pulsars and these much more luminous fast radio bursts, this gap started to be filled over the last about a year by studying the galactic magnetar SGR 1935 plus 2154. This is the magnetar that famously produced the bright FRB-like radio burst last year. So clearly neutron stars can produce emission over a large range of timescales and luminosities. And it's also apparent on this diagram that there's this gap in the parameter space with no known transients. Most fast radio burst searches search at like 100 microsecond to millisecond time resolution. Sometimes they go down to 10 microsecond resolution. But yeah, maybe there's transients in the nanosecond to microsecond time scale that we're just not searching for. So our group performed follow-up observations of chime repeating FRBs with the European VLBI network. So the EBIN is a global network of radio telescopes that use very long baseline interferometry to create high spatial resolution images of the radio sky. We also have an ongoing project called PRECISE. The idea here is to have an ad hoc EBN array with a sample of dishes that at that given moment are not being used by the EBN. The advantage to PRECISE over regular EBN is that PRECISE, usually we can get a lot more on sky time, which comes at the cost of number of antennas per observation. And the main goals of our EBN campaigns and PRECISE campaigns is to precisely localize FRBs, so to study their host galaxy, to study where they're coming from in their host galaxy, and to really probe the immediate environment around the FRB. And these can give us clues about the progenitor of fast radio bursts. We record the baseband data of the individual telescopes. And so if we detect a burst, we can perform a really detailed burst characterization by probing really high time resolution, frequency resolution, and by studying the full polarimetry of the bursts. And then finally, because with PRECISE we can get a lot of on sky time, we can perform high cadence monitoring of interesting targets to try and discover really rare events from these sources. For this talk, I'll focus on how we use the baseband data to study the bursts in high detail, and I'll refer you to Benito and Wolfgang's talk who will present the localization of FRBs with the EBIN and also high cadence monitoring of interesting targets, respectively. So first, I'll start with FRB 2018-0916b, or R3. We're starting to see observationally a characteristic description of repeating FRBs in the burst properties. This might help to classify FRBs into subpopulations, or maybe that will confirm that repeaters and non-repeaters are physically different. For R3, we see that the bursts are narrowband, and in fact, in the recent CHIME FRB catalog, the Plonis et al. Paper showed for a large sample of bursts, repeaters are in general more narrowband than non-repeaters. We also see this trombone effect, which is only really seen in repeating FRBs. And then in terms of the polarimetry, we see about 100% linear polarization. So that's the red curve here, where black is Stokes' I. And we see 0% circular polarization. And then in terms of the polarization angle, which are shown in the top panels, they're roughly constant during the bursts and also between bursts. These properties are also seen in the case of the first repeater, 121102. But I should note the caveat of the Leo et al. Repeater, which some of the bursts from that repeater show lower linear fractions and some show polarization angle swings. But yeah, a large sample of those bursts do match these properties that I've described. And down the line with a larger sample of FRBs with polarimetry, that will be really great in exploring any kind of characteristic polarimetric signature in FRBs. So in burst B3 here, you can see that there's two sharp components in this 64 microsecond profile. So this is the same profile with the dynamic spectrum. If we zoom in time, so from 64 microseconds to 16 microseconds, we see the same two spikes where the second has split into two. If we go a step deeper to 1 microsecond resolution, where the orange and the purple zoom ins are shown below, we see that the first component is actually split into two, each of width about 3 to 4 microseconds. Not all of the bursts in this sample resolve down to these microsecond structures, and actually we see a range of different timescales with a dynamic range of timescales about a factor of 500. And also on these really short timescales, we see subtle but measurable variations in the polarization angle, which is shown in this plot here. Potentially, these are also characteristic of repeating FRBs. So in terms of progenitor models and the emission physics, so if we assume that the FRBs come from magnetars, there are different flavors of magnetar models, which I've broadly characterized here into magnetospheric, so coming from within the magnetosphere, and non-magnetospheric. So for example, a shock that propagates out, interacts with the circumstellar material. In this case, we've measured 3 to 4 microsecond timescales, which implies that the emission region is less than about 1 kilometer if we ignore relativistic effects. And these small emission region sizes are most naturally explained in the magnetospheric model. In these observations of R3, we are limited by scattering from the Milky Way interstellar medium. So that's due to the low galactic latitude of FRB 2018-0916b. But this other FRB 2020-0120e is at much higher galactic latitude. And so the effect of scattering is much smaller. It means it's a really great source for constraining the shortest temporal features. And I also should note that both of these FRBs are localized. FRB 2020-0120e is the FRB found in the globular cluster in M81 at a distance of about 3.6 megaparsecs. So it's also an extremely nearby source. And yeah, I'll refer you to Benito's talk if you want to learn more about the localization. So these are the 4 bursts that we detected during our EBIN campaign of FRB 2020-0120e. And as you can see from the dynamic spectra, burst profiles, and polarization angle, they match all of these repeater characteristics that I described a few slides ago. The time resolution that I've used for plotting here is 8 microseconds, so it's already really high time resolution. Already you can see that there are subtle variations in the polarization angle on these short time scales. As I mentioned in the previous slide, the expected scattering is much lower for this source than for R3. And actually we are not limited by scattering at this frequency, but we're actually limited by the data itself. So I'm gonna pick B2, B3, B4 here, which have sufficient signal to noise to study at even higher time resolution. If we go a factor of 8 deeper to 1 microsecond, you can see that burst B3 really has clear microsecond structure in this burst compared with B2 and B4, which don't really show any structure. So we're gonna zoom in again on B3 and we're gonna go to the highest resolution that we can with the data, which is 31.25 nanoseconds, where yellow and blue are zoom-ins on the profile. And you can see that there is clear 1 to a few bin structures in this burst profile. Now, it's not quite as simple as concluding that this really bright feature here is resolved emission in the burst profile, because any modestly broadband signal will have statistics like this. So in order to prove that this is a real isolated shot, what we have to do is we have to prove that it cannot possibly have come from the local amplitude modulated noise distribution. So here, again, I've plotted the 31 nanosecond profile with a zoom in below on this bright feature. And the green represents this local region that I mentioned a few sentences ago. So this is about 3 microseconds window here. And the reason for taking a 3 microsecond window as opposed to something bigger or even the entire burst to determine the distribution is because we don't have a priori knowledge of the shape of the burst envelope. So we don't know how quickly the envelope is fluctuating. What we do know is in the 1 microsecond profile, there is microsecond structure. So in order to ensure that we are capturing the local distribution of we're capturing the local envelope, as well as having enough samples to make a distribution, we take this 3 microsecond window. Here I show the PDF and the CDF, and from this we can draw a probability that this bright 2-bin wide feature is drawn from the local amplitude modulated noise distribution. And we find the p-value is 2 × 10⁻⁶. So we therefore conclude that this bright feature is in fact a real isolated shot in the profile and is not consistent with the amplitude modulated noise distribution. And this is 2 bins, so it's about 60 nanoseconds. And that's consistent with the expected scattering from the Milky Way interstellar medium. So for NE 2001, the predicted scattering is about 50 nanoseconds. And from our scintillation bandwidth, we predict about 27 nanosecond scattering.
About 3 minutes, Kenzie.
Thank you. From this 30 nanosecond profile, we compute the autocorrelation function in time to measure different time scales that are seen in the profile. We have a time scale that's consistent with the burst width in time. We have a time scale that's about 1 or 2 bins, which is consistent with the really short features that you can see in the high time resolution profile. But then we also have this intermediate time scale that's about a microsecond. And in fact, some crab pulsar giant pulses show nanosecond duration shots that are clustered into microsecond bursts, nanoshots and microbursts. But not all crab giant pulses resolve into these nanoshots and microbursts. We see a range of timescales, and that's consistent with what we see here. So burst B2 and B4 in our sample, these are plotted at 1 microsecond and then 30 nanoseconds, and there's no clear evidence of any microsecond or sub-microsecond emission in this burst. For R3, we measured that there was a range of timescales with a dynamic range of about 500. For this FRB, we find also a range of timescales with a dynamic range of about 1,000. So definitely comparable with the results from R3. So I'll come back to this transient phase space diagram from the beginning of my talk, but now add the timescales measured from these FRBs. This FRB in M81, we've shown based on the polarimetry and based on the spectral properties that it has an observational link to other extragalactic repeating FRBs. We see submicrosecond structure with a brightness temperature compatible to the brightest Crab nanoshots. And we also see microsecond structure, which is seen in Crab pulsar giant pulses. Similar to the Crab pulsar giant pulses, not all of them resolve down to these nanoshots and microbursts, but we see a range of timescales. And these widest components actually have a luminosity 1 or 2 orders of magnitude weaker than the bright FRB-like event from the galactic magnetar SGR 1935. So this source is observationally bridging the gap between FRBs, the Crab pulsar, and galactic magnetar. And it also highlights that there's likely a population of these ultra-fast transients up in this top left of this plot. And so with that in mind, we performed a research of the Green Bank Telescope Breakthrough Listen 121102 data in Gajar et al. 2018. What we did was we went from, in the original search, the time resolution was a few hundred microseconds, and we increased that to microseconds. And we also coherently de-dispersed the data to remove or to limit the effect of dispersion smearing. And in this search, we actually found new bursts. So this is work that's led by Mark Snelders and also bachelor students Zakaria bin Salim and Lars Van. And yeah, these bursts are incredibly narrow, with this burst having 3 components, maybe about a few microseconds wide each. The work I've discussed up to this point has been, we've detected bursts with lower resolution data, studied them at higher resolution, and found narrow structure. This is a search for very narrow bursts in data. And yeah, it's shown that there are these really ultra fast transients. And so yeah, we should be studying at these high resolutions. But we should be searching at these high resolutions. And actually current FRB surveys are operating at like 100 microseconds to milliseconds. And so they probably wouldn't see bursts like this. Okay, so to conclude my talk, I talked about R3, which shows microsecond structure and supports a magnetospheric emission. I showed FRB 2020-0120E is bridging this gap observationally between extragalactic FRBs, pulsars, and galactic magnetars. And we've discovered new bursts from 121102 by searching at the highest possible resolution. We are exploring this parameter space and venturing into very short timescales that's relatively unexplored. And it shows that neutron stars can produce emission over a wide range of times and luminosities. And it really emphasized the importance of baseband data in FRB studies. Thank you.
Excellent. Kenzie is on hand to answer questions, right? So the first question we have, Kenzie, is from Mohit. And he says, it's a very nice talk. Can we deduce anything interesting about the location of the FRB, hence the M81 globular cluster, within the M81 halo from your spectropolarimetric analysis? So is the globular cluster in front of or behind the extended H1 disk of M81?
Yeah, okay, so I guess you would want to probe like the scattering in the burst if you want to see if there is scattering that's in excess than what you would expect from the Milky Way. And yeah, I think the issue there is that the expected scattering from the Milky Way interstellar medium is, as I said, about 50 nanoseconds from NE 2001 or 27 nanoseconds from our measured scintillation bandwidth, and the resolution of the data is 31.25 nanosecond resolution. So they're all at about the same time scale. We are working with Jim Cordes and Stella Ocker to do kind of skewness analysis on these bursts, similar to their work on 121102, which will probably put a limit, like an upper limit on the scattering. But yeah, I think you would probably need much higher resolution data, see the scattering tail to determine if you have anything in excess of what you would expect from Milky Way interstellar medium scattering.
Yeah, and Stella's work shows that, for example, the M81 halo is probably not likely to contribute very much.
Yes, exactly. Yeah.
Other questions? I'm not seeing any in the Q&A right now or on Slack. We'll give it another 10 seconds if someone has something they want to mention. All right, if not, thank you very much, Kenzie.
Thank you.
Okay, moving along to the next talk. This is Danica Scott talking about measuring the coherence of fast radio bursts at high time resolutions. And this is a recorded talk. If any one of the team members are available, please let us know in the chat so that we can do live Q&A afterwards. Take it away.
So yeah, hi everyone. My name's Danica. I'm a second-year PhD student at the Curtin University node of ICRA, and I'm a member of the Craft Collaboration. So what my talk's going to be concerned about is, looking into the emission of fast radio bursts. And what we do know about it is pretty simple. We know that it can't be a thermal process that produces FRBs. This is because knowing the distances to FRBs means that they must be extremely bright transients. And if you calculate brightness temperatures, you get temperatures in excess of 10 to the 35 Kelvin, which is just too absurdly hot to be considered realistic for a thermal process. So the emission must be from some coherent mechanism and not a random thermal one. And so basically the question that I'm sort of talking about is can we measure this coherence and what are the statistics of the emission? And answering these questions is going to be really important in trying to figure out sort of what actually the physical emission process of fast radio bursts. So this has been done. This has been done for pulsars in the past. So General in 2001, they measured 4 pulsars at high time resolutions of 50 or 100 nanoseconds, depending on which pulsar. And what they did is they took many thousands of pulsar pulses and averaged their statistics over all of those pulses and calculated this quantity called the modified coherence function. Here it is m sub s in units of, as a function of pulse phase, which is on the x-axis of each of these plots. Now, I don't really have time to explain in detail how this quantity is, calculated beyond it's to do with the autocorrelations of many averages of autocorrelations of pulsar pulses. But basically, if you have a value greater than 0 at a pulse phase non-zero, you've measured non-Gaussian and coherent statistics, which is the case conclusively in at least 2 of these pulsars. Smits et al. In 2003 said that this might be scintillation. So this is a bit of a question mark because scintillation can also produce a value greater than 0. But the principle is there that you use the statistics of the emission in order to learn something about the coherence of the emission mechanism. And as we just heard, that Nimmo et al. This year showed that there was a forest of shots in a burst from the repeating FRB 2020-0120E, very similar to crab giant pulses and resolved out in an individual shot, which is great because this is a measurement and a confirmation of a coherent emission mechanism, because there's no way an uncoherent thing could create a shot on this sort of time scale with these statistics. But the thing is that repeaters are generally, we've sort of learned recently from the CHIME catalog that repeaters are generally morphologically different to non-repeaters, in that they're generally wider and broader and spread out more in time. And also, if you want to study the statistics of non-repeaters, you probably need a more statistical method you can apply to any FRB in general, not just the ones that you happen to see have a forest of shots. So basically that's what we're setting out to do. We're going to do this, or we've done this through the second order intensity correlation function. This is a function that basically describes the second order correlations of the electric field that you measure for a transient. It's denoted by G2, and it's in units of a time lag tau, which is in units of whatever time resolution you have. And it's basically the average order correlation of your intensity that you measure, averaged over time, divided by the average of the intensity squared. And the basic idea is that you can take this second order intensity correlation function and predict a value for it for what you would expect for incoherent radiation. And given that we know that FRBs in general are polarized, at least partially, we can predict what value you would expect for incoherent, partially polarized radiation, which is what we have at the bottom here. So at a time lag of 0, you would expect the second order intensity correlation function for incoherent radiation to turn out to be 1.5 plus half p squared, where p is the polarization fraction of the transient at a certain time. So that's the basic principle. And so with ASCAP, we've been able to measure fast radio bursts at incredibly high time resolutions. So this figure on the right is FRB 18, 11, 12, plotted with a time resolution of 4 microseconds, but our data in general goes down to just under 3 nanoseconds across a bandwidth of 336 megahertz. ASCAP operates and finds FRBs at an essential F frequency of about 1 gigahertz. It does this by capturing the voltages in the antenna at the time of detection, which allows you, among many other things, such as obtaining accurate arcsecond positions for FRBs. It also gets you full polarimetric measurements of the fast radio burst at a high time resolution. And this is for repeaters and non-repeaters. At the moment, we have this high time resolution data for 15 bursts from 12 FRBs, including 1 repeater. And it's this kind of data is really important for understanding fast radio burst emission, because without it, you have something that looks a bit more like what's on the left. On the left here, this is the same FRB, but at a time resolution of 1 millisecond instead. So if you have only 1 millisecond data for an FRB such as this one, you would think that it's just, a single spike, and you wouldn't be able to resolve out the features in here that you can only see at high time resolutions. There's actually 4 peaks in this time series on the right here that are, statistically significant, which would just be impossible to resolve out without, microsecond at least time resolution. So this is a sort of ensemble of 8 of Kraft's FRBs at high time resolutions. Each of these panels is the intensity in sort of arbitrary units and not to scale, so the peaks of each are not all at the same level. And on the x-axis is the time in milliseconds. And in the title of each of these panels is a little time resolution, and that's the time resolution that this data has been plotted at. So there's a wide range. We have in the top left, we have 10 microseconds being used to plot, and in the bottom left, we have 500 microseconds being used to plot. So these FRBs are very, very varied in their widths and also their morphologies. And there's lots of features that would just be unresolvable without high time resolution data. Whether it is multiple components or even this very gradual ramp up that isn't so sharp in FRB 2020 1124A, which is a repeating FRB as well. So FRB 18, 11, 12, to come back to this one, is a very good candidate for trying to measure coherence statistics. This is for several reasons. Mostly, it is very bright. So when you plot it at 3 nanosecond time resolution, it still shows up. It's still really easy to see, which is it's a sign that it's a super bright burst. So on the right here, this is again the intensity versus time, but at 3 nanoseconds time resolution. And if we zoom in, just for instance, you can see that you can see the individual samples, and within a single 3 nanosecond sample, you have a lot of signal going over your noise. It also has very little scattering for an ASCAP FRB. It's about 50 to 75 microseconds wide, and it has distinct polarization properties. And given that we are depending our investigations and coherence on having partially polarized sources, obviously you would like to have something that is polarized to investigate. So when it comes to actually sort of attempting to measure the coherence of this burst, the method is basically this. So you take your 3 nanosecond data and you divide it into bins that are 336 samples wide, which is, one bin is exactly 1 microsecond. And then in each bin, you calculate the average Stokes I, the polarization fraction from the Stokes parameters I, V, and L, where V and L are the circular and linear polarizations respectively. You calculate the actual value of G2 at 0, and then you calculate your prediction, which is based on the polarization fraction P, and then you compare these last two quantities to see if they match up. I should note as well that this sort of the width of your bin is somewhat arbitrary. That there is a trade-off in that you want to have a bin narrow enough that you can resolve the burst and make sure that you have as much signal and as little noise in each bin as possible. But at the same time, the narrower your bins are, the sort of more spread there will be in your statistics. You want to have as many samples as you want to calculate an average and a variance and that sort of thing, so that you can be more confident in the value that you get out and have basically lower uncertainties. So when we do this, when we apply this with 1 microsecond wide bins, this is kind of the result. So going from top to bottom, in the top panel is again the Stokes I versus time, with each bin being a microsecond wide. In the next panel is the polarization fraction P, and you can see that, yep, this is a fairly strongly polarized burst. It comes up with the intensity as expected. In the third panel, the red line is the predicted value for G2 given incoherent radiation, and the black line is the value actually calculated directly from the intensity in each bin, with a 1 sigma error region surrounding the line. And the final panel at the bottom is the residuals. And as we can see, the results are the value for G2 is completely consistent with that expected for incoherent partially polarized radiation. There is no significant deviation in the residuals, and the curve follows the red line quite perfectly. So that means that the statistics of 18, 11, 12 that we have are consistent with incoherent radiation, but that doesn't mean that the burst itself was incoherent. What probably is happening is that scattering is simply too strong at ASCAP frequencies. So even though 18, 11, 12 is a remarkably narrow burst and remarkably unscattered for an ASCAP FRB, it might just still be too much. And like scattering really is a pain. Like it scales with frequency to the -4. So when you get down into these mid to low radio frequencies at about 1 gigahertz, it really starts to ramp up. So what you would need in able to apply this and expect scattering to not be such a problem, you would need an exceptionally unscattered burst, which is not impossible. ASCAP is finding more FRBs, and maybe one of them will be completely unscattered and unscattered enough in order to detect coherence in it. Or you can apply this method to similar polarimetric data at high time resolutions and higher frequencies, so that you have less of a problem with scattering. But it is really important that the data is polarimetric and at high time resolutions. The higher, the better. And basically just wanted to put a call out there that if you have data like this for any FRBs, then please do get in touch. I would love to work with you and sort of get something out of this and try and apply this method to investigate the emission mechanisms of fast radio bursts. So message me on Slack or send me an email if you would like to get in touch. So yeah, thank you.
Excellent. Just as good the second time round. I don't see Danica around, and I have not heard from any team members. So please do put questions in the Slack for her. And I see Vivek has already put a question there. Please do leave questions there and hopefully we can get some answers. Meanwhile, we'll just keep right on going. So I think if we go on to the next talk. Our next talk is by Vivek Gupta at the Center for Astrophysics and Supercomputing at Swinburne. And Vivek is around, so if you leave us questions, he can answer them live immediately afterwards. Go ahead.
3 minutes left.
Sure, thank you. Okay, good afternoon, good evening, or good morning, everyone, wherever you're listening from. I am Vivek, a final year PhD student here at Swinburne, and I have been working with the Atmos radio telescope for my PhD. So Atmos is a 1.6 kilometer long cylindrical cross interferometer located 50 kilometers east of Canberra. Here in the Google Maps image, you can see the two perpendicular arms. The east-west arm has been in operation for the past few years. There's the north-south arm is just coming online. The east-west arm is divided into 352 individual modules, each of which have a field of view of roughly 8 square degrees. The 352 individual modules or elements are phased together to form 352 tide beams, which fully tile the primary beam of the telescope. We currently operate at a center frequency of 835 megahertz and have a bandwidth of 31 megahertz. Atmos has been running multiple FRB search surveys over the past 5 years. We use a GPU-accelerated redispersion algorithm known as Heimdall, and we also use a machine learning-based real-time classifier, which enables voltage capture at native resolution. If you have been listening to the last 2 talks, I don't have to convince you that having access to native voltage resolution data is extremely valuable. It allows us to coherently disperse the signal, which reveals the intricate temporal and spectral features in FRB. For example, the FRB here presented by Farah et al. 2018. Not only do you see intricate temporal and frequency structure, but also importantly, for this talk, you are able to measure the scattering timescales accurately. The measurement of scattering timescales would not be accurate. Scattering timescales would not be possible if you did not have coherent dispersion applied to your data. You would most likely measure large scattering values correctly, but the small ones you would only get upper limits. And also, if the structure is not deconvolved, then you're also likely to get biased scattering values to a larger number. Okay, as an update, a new convolutional neural network-based multi-stage detection and classification pipeline is currently under development by my colleague Ayushi Mandlik. For more details, I would like to suggest you all to go through her poster, which is currently on display. Some interesting updates on the north-south arms commissioning will be presented by Adam Deller, who will be giving a talk on 3rd of August. Okay, now coming back to the results of the latest FRB survey, which has been running for the last couple of years, we have detected 7 new FRBs showing a wide range of spectral temporal properties. However, one FRB 19117, is a special one. And we look at it in the highest time resolution available. After coherent dispersion, of course, we find that the burst is just resolved at 10 microsecond resolution. It has multiple components. We model it as 3 Gaussian components convolved with an exponential time scale. And we find that the brightest component, which results in which is responsible for most of the signal to noise of the FRB, has an intrinsic width of just 26 microseconds, a small scattering scale of 20 microseconds, and this is despite having a large total DM of 715 parts per centimeter cube. If we subtract the Milky Way contribution, we are still left with a large extragalactic DM of 570 parts per centimeter cube, which we use to place an upper limit on the host galaxy of 0.57 redshift. Okay, so while analyzing the data, there were 2 important questions that were coming to the mind. So first one was because of the fact that the burst had a signal to noise of 30 in the voltage data, while it only had a detection signal to noise of 9.7 in the search mode data. Just barely managed to detect it. So the obvious question is, how many narrow width FRBs is the survey missing? This is the same question which I think Clancy was asking the questions after the previous talk. And the second question that we thought about is, the burst emission seems to have traveled roughly 3 gigaparts across the universe and exhibits only 20 microseconds of scattering. What is this origin? What is the origin of the scattering in this FRB and in FRBs in general? I'll mention that this 20 microsecond of scattering is small, but it is still many orders of magnitude larger, or at least 2 orders of magnitude larger than the predicted scattering from the Milky Way ISM in this direction. Okay, so and I'll try to address both of these questions in my talk today. So jumping onto the first one, how many FRBs is a survey possibly missing. So the fluence detection threshold of a survey is inversely proportional to the square root of the width. So if our survey had infinite time and frequency resolution, the fluence detection threshold, shown by the green plane here, would be simply following a square root width relation. So here is the width, here is the DM, and here is the fluence detection threshold. However, because of the finite time and frequency resolution, the finite time sampling and the beam smearing in the final channels come into play, and the actual detection threshold of a current survey stops decreasing with width, and this orange plane shows what the actual detection threshold of our survey looks like. Now we can convert these detection threshold planes into energy threshold planes, the intrinsic energy of the burst threshold planes, if we assume that the DM of the burst is a proxy for the distance. Now here, we can model the intrinsic energy distribution of the FRB population at a given width and a DM as a power law. And when we integrate along the z-axis, what we get is a 2D map of the fraction of FRBs that our survey is detecting, as opposed to an ideal survey with the same sensitivity would detect. So here is an example map for the Atmos telescope, where we find that at milliseconds width, our survey would be detecting as many FRBs as the ideal telescope would detect. But as soon as the width starts decreasing below the sampling time of our instrument, we rapidly start losing those FRBs, or I should say we are inefficient at detecting narrow width FRBs. At the width of this FRB 1911-07's brightest component and the DM, we find that our survey is detecting only 10% or 10 to 15% of FRBs. So this means that this FRB is quite a special one. And if we could look at some other major surveys that are currently active, for example, the ASCAP incoherent survey, time FRB survey, the superb survey, fast super survey, fast at Parks, these also don't do much well, and all of them seem to miss at least 80% of FRBs with widths similar to 1911-7B. So therefore, detection of a single event at Atmos suggests that a significant population of narrow width FRBs may exist and remains unexplored so far. Now, this obviously is consistent with what Nemo and Danica have emphasized. So this is important to keep in mind, and probably future surveys should be designed with trying to explore narrow width FRB population. This point becomes more important when you realize that at a given fluence, narrow FRBs coming from large distances are more likely to be detected than the wide ones, simply because they will have a higher signal to noise with a constant fluence. And therefore, our best chance at finding high restricted FRBs may be these narrow width FRBs. Okay, so having addressed that, now let's look at how can we use the one event that we have detected to do some science. So first of all, we'll just give you some basics of what scattering is. So scattering is caused by multipath propagation of a wave through turbulent ionized media, frequently observed in emission from galactic pulsars as decaying exponential tail. This is an example of an FRB that shows a similar exponential decay timescale, and it is known to be caused by power law density fluctuations in the ionized medium present on the line of sight. The observed scattering timescale is directly proportional to the scattering measure of the ionized medium that is present along the line of sight, and scattering measure quantifies the path integral of the amplitude of turbulence along the line of sight. Now, McQuart and Coe 2013 gave a relation between the observed scattering timescale and the scattering measure of the scattering medium, which we can directly use for the FRB 1911-07B to estimate the scattering measure of the scattering medium. Now, if we assume that IgM is the dominant source of scattering, then we can directly compute the scattering measure of the IgM for this FRB. However, there is a lever arm effect, which is quantified by the D effective number here. It basically says what is the effective distance to your scattering screen. So based on, we have no handle on where the scattering screen may be, and therefore the estimated scattering measure of the scattering screen follows this curvature, which as a function of the location of the scattering screen, where the dashed line denotates the expected redshift of the FRB host galaxy. if you expect that the IGM scattering is IGM is homogeneous and the scattering is spread across the whole region, and instead of being coming from one scattering screen, then it makes sense to use halfway between the source and the observer as the D effective, and then you get an upper limit on the scattering measure of the IGM. This is an upper limit because here we are assuming that the IGM is contributing all of the scattering. However, it may be possible that the host galaxy and the Milky Way do add a little bit of scattering, and therefore the IGM's scattering measure becomes an upper limit. Nonetheless, this value 2 times 10 to the 13 of scattering measure is 2 orders of magnitude stronger than the existing limits that have been achieved previously using measurements of the angular broadening of intraday variable sources. Okay, so this FRB, this narrow FRB showing a narrow scattering timescale has put a limit on the amount of turbulence in the IGM. However, when we look at other FRBs, they show much larger timescales, then it's unlikely that the IGM would be able to explain the scattering in those FRBs. So, however, to investigate this further, if the IGM has anything to do with the scattering in all those FRBs, then we do expect to see some indication of a DM tau relation in the FRBs. So we model all the FRBs that Atmos detected with coherent dispersion using the same methodology as described for 191107B. Here it is important to note that when we are building a sample of scattering measures, there will be 2 kinds of biases in your sample. One is the detection bias, where you would be missing the highly scattered FRBs. Your detection pipelines are largely incomplete to wider bursts. And also high DM and narrow width FRBs, your pipelines will be missing because of increase in width because of DM smearing. And the other bias is the measurement bias, where, as previously mentioned, if you do not have access to coherently dispersed data at high time resolution, you would not be able to properly measure the scattering timescales of your detected bursts. So using voltage data FRBs, we managed to mitigate most of the measurement bias in our sample. However, the detection bias is unavoidable at this stage, and we need to design surveys with better survey completeness. 3 minutes left. Okay, okay, thank you. So keeping those limitations in mind, we try to fit a power law model to our sample. We actually add all those FRBs detected at POX or ASCAP or other telescopes which have voltage data available with them, and the scattering timescales have been measured after coherent dispersion. So we add those FRBs to our sample, and then we fit a power law model to the data, and we find that the power law model does describe our data pretty well. However, we compare the evidence of such a fit to fitting a model which has no relation. Basically, we force the power law index to 0, and then we fit the data. And when we compare the evidences for the 2 fits, we find that our data only provides a very marginal evidence in support of a DM tau relation. And therefore, we cannot claim that the IGM has anything to do with the sample of FRBs we have detected. This finding is consistent with the findings of Ravi et al., who had used POX sample of FRBs to find weak evidence for such a DM tau relation. Also consistent with Q et al. 2020, which found no evidence for such relation in ASCAP bursts. And recently, we heard from Pragya Chawla that Chime FRB have also concluded that IGM is an unlikely source of scattering in their sample of FRBs. In addition to IGM, recently Ocker et al. Have published their results where they have used the scattering measurements from repeating FRBs in the nearby universe and have constrained placed strong limits on the amount of scattering expected from the Milky Way halo and the halos intersecting line of sight of some FRBs. And therefore, that limitation is also of the order tens of microseconds, again making the halos of galaxies and Milky Way unlikely source of the scattering of the order milliseconds observed in many of our FRBs. So we turn our attention to the next possible source of scattering, which is the host galaxy. Now, it could be the interstellar medium or the circumambient environment of the progenitor that produces the scattering. If it is the ISM, we would like to compare it to the ISM of the Milky Way because there is a well-established DM tau relation for pulsars in the Milky Way. And in this figure, the black points are now the Milky Way pulsars. Yeah. So, and the red points are the FRBs that in our sample. If you want to compare the scattering timescales directly, we need to keep in mind that the FRBs are actually coming from a large redshift. Therefore, the rest frequencies have been redshifted and the time has been dilated. So we correct for those factors by scaling the frequency by a factor 1 plus z, and the tau scales as frequency to the power 4th, and therefore the observed and the time dilation is directly proportional to 1 plus z, leaving us with a simple scaling law of tau is proportional to 1 plus z cube. So when we scale our FRBs with this relation back into a regime where the DM left is in the range expected for the DM host, that is roughly 10 to 100 units, we identify this gray region where the scattering values and the DM values would be the values that an observer inside the host galaxy or just outside the host galaxy might expect to see for these FRBs. Now it becomes immediately obvious that this gray region is many orders of magnitude higher. The scattering values in these regions are many orders of magnitude higher than the scattering values that are predicted to originate in the Milky Way's ISM. Therefore, to have the ISM of the host galaxy explain the scattering in all of our FRBs, we need the ISM of the host galaxy to be many orders of magnitude more turbulent than the ISM of the Milky Way. And this might have been possible. However, the increasing sample of localized FRBs have shown that they are originating in a wide range of galaxies, some being lenticular, some being elliptical, and some being spiral. And therefore, there is no tendency of FRB host galaxies to be associated with high star formation or very dusty galaxies. Then it is possible that it's not the ISM. The ISM of the host galaxies is not particularly special, but it's the circumburst environment which is causing most of the scattering in the FRBs. If that were the case, then we can again use the same equation and calculate the expected scattering measure of the circumburst environment. And we get a value which is much higher because of the lever arm effect than the IGM value. However, despite being a large value, there are exceptional lines of sight in the Milky Way. For example, anostate to the Vela pulsar and to a few extragalactic sources as well identified by the 8001 model, where the scattering measure values to these environments are large enough that they are comparable in order of magnitude to the scattering measures that we require for the scattering time scales that we see. Okay, so finally, if this indeed were to be the case that the circumburst medium is dominating the scattering measurements, there might be a rotation measure tau relation in the FRBs, since the rotation measure is also dominated by dense ionized environments, and so would be tau in this case. So this is a potential line of research that might be explored in the future. So at the end, I would like to conclude by bringing back the points that the current FRB surveys are inefficient in searching for narrow-width FRBs. Detection of 1911-07 suggests that a population of such FRBs may exist and can be useful to probe the properties of the intervening ionized plasma. And FRBs detected at most do not support a DM tau relation in FRBs. The circumburst environment is the most likely source of scattering. With that, thank you guys for listening.
Well, excellent. Thank you again, Vivek. Vivek is around to answer questions, so please leave us questions in the Q&A. And Vivek, we do have one about an observational selection effect from Sergei Popov. The question is it easier to miss a narrow burst in a blind search in comparison to monitoring of repeaters? Or is there no difference between these two situations?
Good question, Sergey. So I think it depends really on the way you're searching for these bursts. In principle, if your search pipeline are identical, then they would be the same. You would miss both narrow bursts from both repeaters and non-repeaters equally. However, because you know the DM of the repeaters a priori, it's easier to design a survey which specifically targets the DM range. For example, I know that the follow-up observations of ASCAP FRBs undertaken by Praveer using the UWL date band at Parkes does use coherent dispersion at the time of searching, which makes it more likely for them to detect narrower bursts. So you can make your searches more sensitive to narrow bursts for repeaters. It's harder and requires more computational cost to do it for blind searches. But if you don't make any efforts, then it will be equally likely, in my opinion.
Yep. Very good. Question/comment from Jason. I think we need to think harder about the fact that FRBs have a wide range of timescales. They don't all just resolve down to nanoshots. What are your thoughts about that?
Yes, I would agree. I completely agree with that. In terms of how do we use that to optimize such strategies is probably the more interesting question in my head, that you want your pipeline to be detecting milliseconds or even seconds duration burst, as we see in the chime case, and down to nanoshots. So you're really searching 6 orders of magnitude of your parameter space, and definitely need to think about it. So yeah, I agree with the comment at least.
It also says something about where the bursts are coming from and whether multiple emission mechanisms might be implicated, or whether you can just do it with scattering at the source versus not, or so on.
Yeah, absolutely.
Yeah, it's interesting. And it is really interesting that they tend to fill parameter space in this way. Very nice talk. Any other questions for Vivek here? If not, or if you come up with questions further, please do leave them in the Slack for the plenary session. And thank you again, Vivek. All right, so we'll move on to the next talk, and I see that we're basically right on time here. This is a talk from Fereshteh Rajabi at the Perimeter Institute for Theoretical Physics, and he's talking about spectro-temporal structure of bursts from repeating FRB 121102A. All right.
Thank you for listening to my talk. I will be presenting the simple dynamical model that basically explains some of the spectro-temporal structure of repeating FRBs. But I will be mainly focusing on FRB 121102A in this talk, and at the end of the talk, I will show a couple of other examples. This is the work that is done in collaboration with Martin Wood's group at Western University. Before I introduce our model, I will just do a quick refresher of some of the spectro-temporal characteristics of repeating FRBs. I will start with the famous sad trombone. Here I'm showing a plot of subbursts of burst 11A of FRB 121102A from Gajar 2018. We have frequency versus time, and you see basically that the central frequency of consecutive subbursts are basically it's drifting and is decreasing with increasing arrival time, what we call sad trombone. We also see this average reduction in the temporal duration of individual subbursts with increasing frequency. And these are just a couple of examples of the basically structure that we have seen in the repeating subbursts. And as more data becomes available, like we can expect new structures and learn more. This basically, the question is if this spectro-temporal, like a kind of a structure that we see for the repeaters can provide some insight about the underlying physical mechanism for this, for the FRBs, basically, or if there are some information that we can extract from these structures. We were motivated by these questions, and we have developed this simple model that basically our dynamical relativistic model, the system is composed of a trigger, an FRB source, and an observer. We basically assume that the FRB source is moving potentially at some relativistic velocity toward or away from the observer. For the simplicity, we assume that basically the observer and the source are aligned along what we call x-axis. The trigger, we also assume that the trigger is seen to be behind the source by the observer. So we have this relativistic velocity. That means that we're going to have a rest frame for FRB, and we are going to have observer's reference frame. At the FRB's rest frame, after the trigger arrives, after some proper delay time, the FRB signal basically follows and is kind of triggered by the trigger source. The time interval that it takes for the FRB signal to emerge after the arrival of the trigger, we call it proper delay time. And the duration of FRB signal is basically the proper pulse duration. To basically, at the observer's reference frame, we can basically look at these time intervals and find them by using the Lorentz transformation of the space and time in the rest frame and the observer's frame, and by accounting for the distance that the FRB source has traveled during these time intervals, basically the top prime D and like the top prime W. We arrive at these simple relationships on the right corner, bottom corner, that we find that TD, which is basically the delay time at observer's frame, is related to the proper delay time at the rest frame times the rest frame frequency nu naught divided by the frequency at observer's frame, as we call it nu observe. And we also find this relationship for the TW, which is the pulse duration at observer's frame. Nu naught and nu observe are related using the relativistic Doppler formula. Here, beta is basically the velocity of the source that we have divided by basically the speed of light. This very simple relationship that we find for the pulse duration and the delay time, they contain very important information in spite of their like a simple appearance. One being that one of the things that we see from the TW equal to top prime W nu naught over nu observe is that for a given rest frame frequency nu naught and top prime W, which basically depends on the properties of the source, we see that the pulse duration at observer's frame scales inversely with the frequency that nu observe. This has been already noted and studied for FRB 121102A. Here I'm showing the plot from Gajar 2018 paper. They are basically showing the time, the pulse duration, pulse width in millisecond versus the frequency of the pulse. As you can see, although there is some scatter in the data, as you go to higher frequencies, the duration of the pulse basically decreases, and this like a inverse scaling is apparent here. So this beside this narrowing of the pulse with increasing frequency, we also have one of the results of this model is basically the relative frequency slope of the consecutive subbursts, delta nu observed, delta TD. If you start from that relationship I had for TD, top prime D, nu naught, nu observe, and take the derivatives of this, basically in terms of nu observe and top prime D, like one of the terms that you arrive, and you allow for some velocity, basically dependency, you arrive at this pink relationship that I show on in the central, like at the center of the page. Basically, what this says is that we have the relative frequency slope, delta nu observed, delta TD, capital, like I use the capital delta, that is a function of basically that linearly scales with nu observed. Here, D nu observed, D top prime D is a systematic parameter that basically depends on the physical properties, like the physical environment of the FRB source. So for a given nu naught, for a given rest frame frequency, we see that the relative frequency slope scales linearly with nu observed. This is basically, this comes out from this equation. And this is basically, this has been also already like investigated in the FRB, for the FRB 121102A data. Here I'm showing the plots from Hessel's 2019 paper. In the left, they are basically showing the frequency and versus time. And they are showing that as the frequency basically increases, the slope, the relative frequency slope is basically scaling linearly with that and is basically increasing. On the right, we are showing they have shown the burst drift rate versus the observing frequency, and the dashed line is the linear kind of fit that they have to their data. And as you can see, they are going for the frequencies that are slightly less than 2 gigahertz. And they are finding the burst drift rate is around like 150 or so. And as they move toward like the observing frequency that is close to 7 gigahertz, they are finding that the burst drift rate is like almost like 4 times or more, around 800. So this has been already studied and shown for the SAT trombone effect for the 121102A, and is consistent and in agreement with what our model basically is predicting too. One thing that we basically derive from the equations of this model is the single subburst slope scaling inversely with the time duration of the subburst. This is again, if we take the relationship that we had for the TD that I show in the bottom right corner, and we take the derivatives, and if we focus on the like a first term as I circle it in pink, and basically we can write down that the normalized subburst slope, which is 1 over nu observed d nu observed dTd, scales inversely with TW, the burst duration. A here is a systematic parameter again. It depends on the physical environment that we have there and basically the properties of the source. So to basically investigate if this law applies to the FRB data and validated and studied, we have applied this to the FRB 121102A data. Here I'm showing some examples from Qajar 2018, Michilli and Josephi data. These are basically some of the data sets that we are using. My colleague Mohammed, that he can see his talk in the next plenary session or the next one. He basically did the data analysis part, so he can answer a lot of questions in that regard. What he did was he looked at these data sets for the FRB 121102A and 2 other repeaters that I will show later on. He used the 2D autocorrelation function technique by Hessel's 2018 to measure the subburst slopes and time duration. The way he did it, he fitted a 2D Gaussian function to data, and by extracting the Gaussian fit parameters, the minor, major axes, the angles, he could basically measure the subburst slope and time duration of the subburst. Here, we are showing the results of the measurements. We have in this plot, we have the normalized basically subburst slope, the 1 over nu observed d nu dTd versus the subburst duration TW here. I focus first on the red like a color data, which is for the FRB 121102A that comes from the Michilli, Qajar, and Josephi basically papers. As you can see, and we have basically applied this like a relation that this law that is basically predicted by the model, and we find that it basically fits these 3 sets of data very well, and we find that the 3 sets of data basically obey the same law between their respective normalized slope, subburst slope, and their time duration. Here, we find that the fit parameter that I'm showing here for the 3 sets of data for the FRB 121102A, the fact that basically as I showed, the fact that the FRB 121102A data basically follows like the pulse narrowing that we saw with increasing frequency, the SAT trombone effect, that basically the drift, the central frequency drift scales linearly with the nu observed. And here that we see that data from 3 different sets of data with different new observed, they are basically following the same law. It basically points out that and can be only explained if the basically the rest frame frequency nu naught is not varying by a lot, and they basically share the same rest frame frequency. So if you look at the bottom corner relationship, if you basically replace for TW in terms of nu naught and nu observed, you can basically see that if the three sets of data basically they're sharing the same law that links the normalized basically slope and the time duration, and we have the same A for them, this can be only explained if the nu naught is not varying by a lot. And this basically hints that a narrow band process, physical process, might be at work, basically producing these FRBs.
I didn't want to interrupt you mid-sentence, but you have about 1 or 2 minutes left.
Yeah, this is like I have one more slide. So now the question, another question that pops up is that, okay, is this law some universal law? Are there more like FRBs, repeaters, that they basically obey this law, or like a category of them that they obey this law? Motivated by this, we basically investigated data from 2 other FRBs, basically FRB 180916B shown in blue with their fit in blue basically dash line, and FRB 180814A in green. And as you can see, the data from these 3 FRBs that basically and their respective basically fits, they all obey this law. The inverse scaling between the normalized slope and the time duration. And the A parameter that we find is remarkably close for this 3 basically data set. This is basically a significant result that the data from 3 different FRBs coming from different galaxies with different like a redshift, different physical kind of environment, they are basically obeying the same law. And it raises the question if this is some kind of universal law between among the repeaters or a population of them, or it basically can be used to categorize them. And is it that is basically pinpointing to the fact that these are, like, as I explained for FRB 121102A, these are basically originated by some kind of narrowband physical process. So this needs to be investigated more, and our colleagues are like looking into more data, and basically if other, like as more data becomes available, we can verify or like learn more about this. So this is the outlook for the work. But before I end, I want to thank the audience for listening to my talk, and also people that they have been very helpful with obtaining and analyzing data, including Jason Hessel, Shiryash, and Ziggy at McGill. Thank you so much.
That was an excellent provocative talk by Fereshteh. They aren't around for question and answer. So if you do have questions, please leave it in the Slack and tag them, and hopefully we can get responses to that. So I think we will keep going. Our next talk is by Daniele Michilli. Daniele is a Banting Fellow at McGill University right now, and he's talking about a search for periodicity in multi-component FRB profiles. Some tremendously interesting work on behalf of the CHIME FRB collaboration. Daniele is around for question and answer with any luck. So if you have, please leave me questions in the Q&A, and we can discuss them afterwards. Take it away.
My name is Daniele Michilli, and I'm presenting my work to search for periodicity in fast radio bursts with complex profiles. I'm presenting on behalf of the CHIME FRB collaboration. As Pragya presented in her talk, CHIME FRB recently released its first catalog, where more than 500 fast radio bursts are presented. With such a large sample, we are bound to find some sources that are unique and can shed a light on the entire population. This is certainly the case for FRB 2019-12-21. This fast radio burst is unique in that it's very long. Its total duration is more than 3 seconds, as you can see on the right plot, where the pulse profile is represented on top, and on the bottom it's waterfall. It's also formed by a large number of components which overlap due to a strong scattering that the source experienced. Given these characteristics, we first investigated whether this fast radio burst could actually be emission from an unknown galactic pulsar. However, its dispersion measure is more than 4 times higher than the maximum value expected for the Milky Way. And also, it is at a relatively high galactic latitude of around 34 degrees, where the models are not expected to have large uncertainties. We searched the localization region for evidences of supernova remnants or H2 regions, but we didn't find any. So we conclude that this source is actually extragalactic with high probability. Given the complex pulse profile, I tried performing a fast Fourier transform to obtain a power spectrum. And as you can see, a clear peak appeared, hinting the possibility of a periodicity at around 200 milliseconds. If confirmed, this will be very interesting to have hints about the emission, the progenitor of this source. However, a power spectrum is not a great figure of merit for a periodicity if there's a limited number of components, such as is the case for a fast radio burst, especially if the components vary significantly in signal-to-noise. Therefore, a proper timing analysis was needed to confirm this, and this in turn requires first to model the complex pulse profile. Given that the components overlap due to scattering, this is not a straightforward task. So what we did was to perform a fit using MC, and we chose a very wide range for the priors in order to avoid any human bias on choosing the initial conditions. And we also tried fitting for a range of components. As you can see in the left plot, we fitted between 7 and 14 individual components to the profile. And we chose the smaller number of components that gave the lowest chi-square within the uncertainties. Now, each component was modeled with a Gaussian convolved with an exponential tail. And the same scattering timescale was used for all the components. After the fit, we found out the best model was given by 9 separate components. So we conclude that this fast radio burst is actually formed by at least 9 components. And the intrinsic width is pretty typical for a fast radio burst. It's around 4 milliseconds, while the scattering timescale is huge. Even though this modeling of the pulse profile is quite simplistic, we find a value for the scattering timescale of 340 milliseconds. which is of course a very high and need to be explained. But most important, this analysis gave us the time of arrival of each component, which we could then fit with a timing model. And in particular, we only fitted for a period. So we didn't use any period derivative or similar. And as you can see in the residuals plotted on the right, this fit was very good. We found that a periodicity of 217 milliseconds gave a very small residuals to the fit. And this means, of course, that we have an integer number of rotations if a neutron star is that is rotating is causing this periodicity. We calculated a significance for the periodicity by generating a large number of random time of arrivals. And in this way, we obtain a significance of around 6.5 sigma. So the chances of obtaining this just by luck, it's extremely low. Next, we tried to find similar sources where multiple components could be identified in the pulse profile and they could be periodic. But we didn't find any example as extreme as in the first case. In fact, the two closest relatives that we identified had 5 and 6 separate components, respectively, and against the at least 9 components of the previous case. We performed a similar analysis as shown you before, and despite the power spectra show some significant hint of possible periodicities, the timing analysis shown in the middle shows that the jitter obtained for single data points is pretty high. And in fact, the confidence for the periodicity estimated on the right with a large number of simulations as done in the previous case only brings the significance to 1.3 and 2.4 sigmas for the two events. Therefore, we consider these additional sources to be interesting, but not significant enough to be included in the rest of the analysis. Next, we consider possible scenarios that can account for such a periodicity. The first obvious model is an extragalactic pulsar that, for an unknown reason, emits a train of pulses for a short period with an extreme luminosity. The period with duty cycle and jitter observed for this source are all compatible with galactic pulsars. However, of course, the luminosity is extremely high and also the scattering is extremely high. If this fast radio burst was emitted by a magnetar, we think that the periodicity favors a magnetospheric origin of the burst as opposed to synchrotron flare models. In fact, the latter class of models wouldn't be excluded by this periodicity, but would certainly require ad hoc assumptions. We explore one scenario in which a pulsar of average luminosity at a distance of 1 gigaparsec, which is the distance estimated from the dispersion measure of the first fast radio burst. A similar pulsar could be observed from Earth. We found that one possible explanation may be that it is gravitational lensed by a compact companion. On the right, we explore the parameter space for such a system, in particular the mass of the companion, the binary separation, and the alignment angle of the system that is required to observe a gravitational lens. We find that a pulsar in orbit with a supermassive black hole could, in principle, explain the observations, but the alignment angle must be extremely small, making the probability of observing such a system unreasonable. Therefore, we tend to exclude such an hypothesis. We also consider the possibility that this periodicity is not a strict periodicity generated by a rotating neutron star, but could be a quasi-periodicity, for example, similar to the microstructures sometimes observed in bright radio pulsar and often in magnetars, where a single pulse from the pulsar is actually formed by a number of quasi-periodic components. However, there are significant differences, other than, of course, the huge luminosity of the fast radio burst. And the first one is that the microstructures don't have a strict periodicity as the one observed in this source. And also they usually require an envelope of emission as opposed to the pulse profile of the fast radio burst that could be modeled with single components. We also consider crustal oscillations that some model invoke as a mechanism for magnetars to produce fast radio burst. Finally, we consider the case that the fast radio burst is emitted by two neutron stars that are orbiting each other and that they are interacting. And therefore, the periodicity that we see is actually generated by the orbital modulation of the two neutron stars. I leave you with a summary of these possible scenarios, and I open the floor for discussion, and I thank you for your attention.
Just a startling and dramatic result from the CHIME FRB collaboration, and Daniele, very nice. Daniele is around for questions, and we do have several questions to go. So Daniele, if you are around, first of all, a question from Brian Metzger. Do you find evidence in the frequency dependence of the width of the scattering tails to be sure that this is actually scattering?
Thanks, Shami. Hi, Brian. I hope my audio is okay.
Yeah.
We actually didn't perform a frequency resolved analysis of the scattering for a few reasons. The signal to noise of single components is not very high. They overlap, and the fact that there are so many makes a similar analysis quite computationally expensive and difficult to perform accurately. So we just relied on the on modeling the pulse profile.
Right. And then a related question from Jason Hessels. what fraction of the CHIME FRB events have scattering greater than 100 milliseconds like this? So is this event in fact twice exceptional, that it both shows a convincing periodicity and is highly scattered?
Yes, it is indeed the case. It's twice exceptional. This is an outlier both for the duration and for the scattering.
Yeah, yeah. Do you have any? Would you be willing to stick your neck out on what that means? You don't have to stick your neck out if you don't want to.
Yeah, I'm not sure. No, well, just, for my head that this source lives in a pretty extreme environment.
Yeah, that seems to be a plausible way to think about it, I guess. Another question from Sergei Popov. He asks, naively, it seems that smooth decay of intensity for 400 milliseconds, which is 2 characteristic timescales, and 600 milliseconds, which is 3 timescales, does not look like a 200. So it does not look like 200 milliseconds is a spin period. Can you actually exclude it?
I'm not sure actually what this means.
Yes, Sergey, do you have a quick clarification, possibly?
Maybe we can discuss further.
Yeah, maybe we can,
because I'm not sure. Sorry.
Yeah, maybe we can take this up in Slack as well. Are there other questions for Daniele? Jason had a question about whether you considered neutron star oscillations after a magnetar giant flare, but you addressed that to some extent in your talk. Do you want to say anything further about it?
Not much. I think they are a valid explanation. So in the paper we comment on them and report that they are a valid option.
Yeah. All right. Well, again, thank you. This is just a startling result, of course, and a very, very interesting paper, which is now on arXiv as well. Thank you, Daniele. We'll go on to the last talk of this session, and this is by Wolfgang Herrmann, and on behalf of a collaboration of people, including Jason, who will be available to answer questions afterwards. So please do leave questions in the Q&A and we can get to them. So Wolfgang is going to talk to us about high cadence multiband monitoring of FRB 2020-1124A and using that to probe the bright end of the FRB luminosity distribution. Take it away.
Well, thanks for listening to this talk. I should mention that there are quite a few people involved in the preparation and the data behind this from the University of Amsterdam and ASTRON and the Chalmers University in Sweden and the Nicolaus Copernicus University in Poland, because it's a multi-instrument effort that will be talking about, and it's about the observation of FRB 2021-1124A. So let's get started by saying, what do we know about this FRB so far? It was detected by CHIME, and it is a known repeater. And the story started essentially when CHIME reported an enhanced activity that was in the second half of March this year, reported by an astronomer's telegram, where they reported this seemed to be in an active phase, and that triggered quite a number of observations by various telescopes who then issued astronomers' telegrams as well. There were quite a few observations in L-band by quite a large number of instruments, but there were also observations, of course, by CHIME itself and by the GMRT and ASCAP on different frequencies that were reported, and also quite some activity of this FRB. What we also know, due to this heavy activity, is where is it located? The host galaxy has been identified, And therefore, we also know the distance. The redshift is a z of 0.098. So it's a fairly close FRB, which is probably also the reason why we see a lot of pulses from that. So this is the sort of the starting point. And the second question is, what is the motivation behind the observation I'm going to talk about? What we're interested in is the energy distribution of FRBs, and of course, this one in particular. The panel here on the left shows FRB energy distribution, which has a flat here because of the limited sensitivity of instruments. Then there's a gradual linear decrease, and then it sort of tails off towards higher energies. So the question is this a multimodal behavior? Maybe is it even time variable? So we see different behaviors at different times. And the question is if it's, that is also seen in other sources, are there different emission mechanisms behind that? Or maybe different emission regions from one source. You have seen this panel on this right-hand side already from the talk by Kenzie. So let me just add a few remarks to that. So essentially what we're looking at is how does that extend the going to very high energies. And also we know, for example, from the SGR 1935 that we can see very large variations in the energy of the pulses, in this case from the magnetar, which extends over 7 or maybe even 8 orders of magnitude. So the question is, do we see a similar extension in the FRBs? Do we have FRBs which show extremely luminous pulses? So this is sort of the background. The point now is, if you want to find very high intensity pulses, they are rare. And typically, if you look at the large instruments like FAST, which is depicted on the right, they see lots of pulses, but they can only spend a few hours or maybe tens of hours on a particular source. And you won't capture the rare and big events then. So you have to take a different approach, a complementary approach, by using instruments that can afford to put time on a single source in hundreds and thousands of hours so that you can capture the very rare high intensity bursts. And this is the approach that we have been taken. The instruments involved in this are 4 instruments. There's the Torun telescope, 32-meter instrument operated by the Nicolaus Copernicus University in Poland. Then we have the Onsala 25-meter dish in Sweden, operated by Chalmers University. Westerbork is contributing with one of their, I think it's 10 dishes of the 25-meter range from the array, operated by ASTRON. And then we have the 25-meter dish, the Stockert in Germany. Just a few words about that, because it's a little bit out of the ordinary. It's not operated by a university, or it's not operated by an institution like the Max Planck Institute or ASTRON. It's operated by volunteers. So it's an association that does that and operates this instrument. It's a group of people who are just enthusiasts, and typically they are retired and gray-haired like myself and just need a big toy to play with. So these are the instruments. We have these instruments on somewhat different observing bands in order to have a wide coverage of different bands. So Torun was basically contributing most of the observation time of their observation time was on C band. They also had some L band operation in the later stages of the observation run. Onsala is operating on L band with 2 different bandwidths. Westerbork was primarily concentrating on the P band, so the low frequency part of that observation. And also it contributed to L band observation, and the Stockert is a purely L band instrument with 100 megahertz of bandwidth. So these were the observed bands. Now, looking at the time and cadence of observations, it's all started with a trigger of the astronomer's telegram by Chime late March. So the first observation was on the 31st of March by the Stockert telescope. These lines show the cadence of the observation and the duration of the observation of the different instruments. Also, the color denotes the band that's used. So Stockert all L band, Turun C band mostly, but some L band, especially in the later phase. Onsala was all L band, and then there's P band, mostly by Westerbork. Now you see a gap in the observation of the 3 telescopes here. This was due to the involvement of these 3 telescopes in the European VLBI network. So they couldn't spend time on that particular source because of other things. Also, during this time, the source became relatively close to the sun. So in our case, the sensitivity was a bit impaired. In total, we are talking about in excess of 1,700 hours of the instruments being on source. We are continuing, so in the meantime, it's even more. So it's a massive investment of observation times. And what did come out of it in this long time of observation? These are the clear detections that we have at the times when they occurred, and the color denotes which instrument contributed or which instrument actually detected it. So you can see that there are 2 events which were simultaneously detected by 2 instruments. One was Onsala and Stockert, and the other one was Onsala and Turun, which were simultaneously detected. I should mention that the 8 events shown here, that these are the ones that are really unmistakably clear events. There are a couple of more where we're scratching our heads and saying, okay, this is sort of a maybe detection, but we're uncertain. It could be also a statistical fluke. So we keep them out of the consideration for the time being, unless we find out that we have some more evidence for that. So it's 8 pulses that have been detected during this time. Once again, the time was from the 31st of March until 10th of July. As you can see, there was a gap in observation, but it was mostly covered by Stockert. And you see that ever since the sort of end of May, nothing more was observed. This is an indication that the activity of this FRB seems to have declined. So if we summarize these observations, 8 pulses were observed. They were all observed in L band. And as mentioned, 2 of these were observed simultaneously by 2 instruments. These observations were done concurrently with different instruments, and we did not detect any P band or C band pulse. Even in cases where we had a strong emission in L band, and P and C band were observed simultaneously. So that's a message that the pulses are essentially spectrally confined, in this case, to the L band. The fluences have been observed. They were in the 10 Jansky millisecond range starting. This is sort of the limit of the sensitivity of these 25-meter instruments. And they went into excess of 1 kilojansky millisecond. So really, really bright pulses were detected. And as I mentioned, there were a few more pulses, or quite a couple of other pulses, where it's just uncertain whether these are real. So we keep them out of the picture for the time being. This is a gallery of the pulses that were observed at Onsala. The strongest one has an excess of 1 kilojansky with 3 components. It's also clear that you can see the scintillation from these pulses. As you can see also in the other events here and here, there's a clear scintillation shown. This might be also a bit of a Z-trombone effect, but it's certainly not too obvious a Z-trombone. So this are the major pulses observed from Onsala. Then looking at what we have observed on the Stockert telescope. These are the two brightest ones. This is actually the first FRB pulse which was observed in this series of observations about mid of April. And this has a peak flux density of 215 Jansky and a fluence of excess of 300 Jansky milliseconds. So it's a very bright pulse. And this has also been reported in one of the astronomers' telegram. Now, about a month later, almost 30 days on the hour, but that's a pure coincidence, there was another event observed, which was substantially brighter even, that had a peak flux density in excess of 400 Jansky, and the fluence is in excess of 1200 Jansky milliseconds, so extremely bright. And I believe that this pulse is probably among, if not the brightest pulse from an FRB ever observed. And if you look at the signal-to-noise ratio, just remind you, this is a 25-meter instrument. It's an uncooled receiver and still an excellent signal-to-noise ratio. There is
about 2 minutes, Wolfgang.
Yeah, there's one remark I would like to make. We have some little dots here. This is an instrumental artifact. This also gives rise to this little precursor, so please ignore that. This is not astronomy. So the conclusions, we have a multi-band observation employing multiple telescopes in order to provide insight into the very high intensity FRBs. We have demonstrated that smaller radio telescopes are suited for the purpose. They can make substantial observing time available and still have sufficient sensitivity to see these very bright pulses. We've seen that the FRB 2021-11A seems to be spectrally confined, at least for these very high intensity pulses, because we haven't seen anything in P and C band. And the activity of this particular seems to have declined since the March-May timeframe. The next steps will be to process the voltage data in order to polarimetry, and we have seen in the talk by Kenzie that high time resolution analysis is interesting, so this will be done as well. And observations will continue. This will include other repeaters, and that has been started and has also been seen in the first results. So we are looking forward to what's going on in the future on these very bright pulses, and I'm happy to take questions.
Oh, thank you. Excellent, excellent stuff here. Herman is not, Wolfgang is not here, but Jason is happy to answer questions on his behalf if people would like to put questions. Jason, I do want to point out that it's amazing to have a volunteer-run professional grade telescope like that.
Yeah, for sure. And they have quite a group of people running it. We have a kind of a similar 25-meter dish here in the Netherlands as well that is run by volunteers, and we're certainly in discussion with them about trying to incorporate that in this high cadence monitoring as well.
Yeah, it's amazing. Like an extension of amateur astronomy to the radio domain with extremely impressive results. We have a question from Darshana Vishrolia. Do you only look at single FRB DM, or do you also do a general DM search for other likely FRBs since your beam is so large?
We're looking at known sources. We do a DM search that's fairly generous, but the beam is not that large compared to CHIME, so the chances of just finding something serendipitously are really actually very, very low. Maybe not completely zero given the large on-sky time, but we're a little bit restrictive in the DM search because we're dealing with baseband data as well, and we're trying to search it at higher time resolutions. We're trying to focus a bit more on finding, really short duration events blindly, as opposed to finding some random other FRB than the one that we're actively targeting.
So the reason you think it's unlikely to get other FRBs is it's not just that the beam is fairly large because for a 25-meter telescope, but it is also a question of it's not very sensitive, basically.
No, it's not very sensitive, yeah. And we think it's more scientifically interesting to start searching the data at like, say, 8 microseconds, or maybe some magical day at 1 microsecond time resolution blindly.
Yeah, yeah. Other questions for Jason on behalf of Wolfgang? If not, please do put further questions in the Slack, and people will pick up from there. And I just want to offer all the speakers a round of applause. It was just as good the second time around, if not better. So thank you, everyone. And there will be another session coming up, I guess, in just a few hours. So see some of you around then. And thank you, Jason.
Thanks, Shami.